The James Webb Space Telescope has delivered exciting news once again. A study unveiled evidence of the first stars, astonishingly 1,000 to 100,000 times more massive than the Sun. For context, the most massive star we know of is only 250 times the Sun's mass. These colossal stars boast core temperatures reaching a staggering 75 million degrees Celsius, which is 5 times hotter than the Sun's. While peering at the edge of time in the early universe, JWST discovered indications of these gigantic first stars in one of the most distant galaxies known to us. This remarkable study holds the potential to illuminate the very beginnings of the cosmos and unveil the last unexplored era in the captivating history of cosmology. But how did astronomers make this exciting discovery? How did they determine the mass of these extraordinary stars? Finally, and most importantly, how will this discovery help us understand what happened when the universe was in its cradle? The first billion years after the Big Bang remains an enigmatic period in the universe's history. It is shrouded with many mysteries that astronomers are still trying to unravel. During this era, the universe was incredibly dense and hot, cramming all matter and energy into a tiny space. As it gradually cooled down, fundamental particles emerged, and around 10 seconds to 16 to 20 minutes after the Big Bang, primordial nucleosynthesis occurred, giving rise to deuterium, helium, and lithium nuclei. Approximately 380,000 years after the Big Bang, as the universe continued to cool, the early nuclei combined with electrons, leading to the formation of neutral atoms in a process known as recombination. Prior to recombination, the universe was too hot for light to shine through. But this critical event freed the photons from thermal equilibrium with matter, making the universe transparent. The light emitted during this era is what we now observe as the cosmic microwave background, or the CMB radiation. Shortly after the CMB was released, a mysterious epoch known as the Dark Ages began, during which no stars or galaxies existed. Little to no information is available about this period, which is believed to have lasted for approximately 100 to 300 million years. During this time, clouds of gas collapsed, leading to the formation of the first stars and galaxies. The evolution of these initial stars emitted energetic ultraviolet light, and other catastrophic events like supernovas or hypernovas also released various radiations. These energetic processes heated the surrounding neutral hydrogen gas, initiating the reionization of hydrogen. This transformation cleared the universe from the overcast of neutral hydrogen gas clouds, rendering it transparent to ultraviolet light. By approximately 1 billion years after the Big Bang, the universe had evolved into a bustling environment filled with bright stars and galaxies, resembling a cosmic zoo with a rich diversity of celestial objects. The exact timelines of the Dark Ages, the formation of the first stars, and reionization are still being researched, and the available observations have shaped the best model of the chronology of our universe. However, the arrival of the James Webb Space Telescope has added more suspense to our understanding of the early universe. With its unparalleled ability to peer into regions of the sky previously inaccessible to the Hubble Space Telescope, the JWST has revolutionized our exploration of the early universe. Webb's observations have unveiled fully evolved galaxies existing at very high redshifts, corresponding to about 200 million years after the Big Bang. This discovery raises two significant questions. Firstly, what conditions in the early universe are we missing in our models that accelerated the evolution and growth of these galaxies? This directly leads us to the second problem, which is the period in which the first stars were born. Did they form around or after 100 million years after the Big Bang? If not, what unique characteristics or conditions of the universe led to the emergence of fully evolved metal-rich galaxies in its early stages? While studying these high redshift galaxies discovered by Webb, some scientists thought out of the box. The study took an innovative approach when the nature of these first stars and their role in the evolution of high redshift galaxies was questioned. This line of thinking paved the way for this research, and it is here that the observations from the James Webb Space Telescope come into play, providing crucial insights into the early universe. The James Webb Space Telescope made significant observations of a distant galaxy named GN-Z11, situated in the high redshift universe. GN-Z11 is one of the most remote galaxies known to us, existing around 440 million years after the Big Bang. Its light has traveled an astounding distance of about 13.3 billion years through the expanding space to reach us. It's worth mentioning that the Hubble Space Telescope had previously discovered GN-Z11 in 2016. However, when astronomers observed GN-Z11 with Webb, they found something strange in its spectrum. The galaxy's interstellar medium exhibited an unusually high amount of nitrogen compared to oxygen, indicating an exceptionally high nitrogen to oxygen ratio. In fact, the N/O abundance ratio in GN-Z11 is about 4 times higher than what is observed in the Sun, and approximately 1 order of magnitude higher than the ratios usually observed in nearby galaxies. But why are astronomers so curious about the abundance ratio? What does it really signify? The abundance ratio serves as a crucial indicator of a star's chemical composition, typically expressed as the logarithm of the ratio between 2 metallic elements in the star relative to their abundance in the Sun. For instance, the abundance ratio of iron to hydrogen is defined as the logarithm of the iron to hydrogen ratio found in a star compared to the same ratio in the Sun. By analyzing these abundance ratios, astronomers can gather valuable insights into the star's origin and evolutionary processes, since different chemical elements in stars are produced through various mechanisms. Additionally, the abundance ratio even provides information about the star's age and core temperature. A famous example is the Great Dimming of Betelgeuse that started in late 2019. During the event, the star's temperature dropped by 80 Kelvin. The drop in temperature was determined by analyzing the ratio of vanadium-1 and iron-1 spectral lines, which had increased by a factor of 1.9. This temperature drop was further confirmed by studying the red supergiant's infrared spectrum. But what is the high nitrogen to oxygen abundance ratio in GN-Z11 hinting at? The peculiar abundance ratios observed in GN-Z11's spectrum find plausible explanations through globular clusters, which are ancient, massive, and densely packed groups of stars known to have formed in the early universe. These clusters can be found in nearly all galaxies, occupying positions in the halo and bulge of spiral galaxies like the Milky Way. Notably, our galaxy contains over 150 globular clusters, while our neighboring spiral galaxy, Andromeda, hosts around 300 of them. Scientific evidence suggests that the majority of stars within these globular clusters were formed through a process involving the mixing of gas with hot hydrogen and other chemical elements expelled by the explosive deaths of short-lived older stars. These older stars, known as polluters, release heavy metals into the surrounding gas, thereby enriching it and providing the necessary conditions for the formation of new stars. This phenomenon has already been observed in globular clusters within the Milky Way. Astronomers were intrigued to investigate whether the same phenomenon observed in globular clusters also applies to high redshift galaxies. This led them to explore the nature of the polluters responsible for the high nitrogen to oxygen ratio, indicative of the presence of nitrogen. It turns out that for a star to produce nitrogen, hydrogen must undergo fusion into helium through a process known as CNO cycle, which requires extremely high temperatures, reaching several tens of millions of degrees Celsius. These conditions can only be achieved by supermassive stars, with masses ranging from 1,000 to 100,000 times that of the Sun. The formation of these supermassive stars is thought to occur within globular clusters in the early universe, which consist of approximately 1 million stars, accreting gas and dust at a rapid rate. This accretion process leads to stellar collisions, resulting in the formation of these massive stars. In-depth studies revealed that this scenario of supermassive star formation aligns with observations of abundance ratios, both in globular clusters and the high redshift galaxy GNZ11. This discovery implies that both globular clusters and GNZ11 possess the same type of polluters, supermassive stars, responsible for enriching their environments with heavy elements like nitrogen. Astronomers have also considered the possibility of Wolf-Rayet stars, particularly those with massive star winds, being potential polluters in GNZ11. In this scenario, the need for supermassive stars is eliminated, as the winds from rotating massive stars are primarily composed of hydrogen-burning products like nitrogen and oxygen. If GNZ11 hosts such rotating massive stars, the analysis suggests that their winds could indeed account for the peculiar abundance ratio observed. However, it's critical to note that this explanation would only be applicable within a limited time interval. While the possibility of rotating massive star winds being the polluters in GNZ11 is relatively small, astronomers cannot completely rule out this scenario. Observations from JWST have opened doors to completely new scenarios involving supermassive first stars. This has helped us improve our understanding of the early universe and the nature of the first stars. But there's one more possible discovery made by Webb that you must know about. Besides the supermassive stars, Webb has also found evidence of the first dark stars in the early universe. Dark stars, forming at the centers of proto-galaxies with a mix of ordinary matter and dark matter, undergo a unique process called annihilation, when dark matter particles collide with their antiparticles, releasing energy. This new study reveals that dark stars are powered by the heat energy produced through dark matter annihilation, in contrast to conventional stars that rely on nuclear fusion. Despite their name, dark stars are predominantly composed of ordinary matter, like hydrogen and helium, with only a minor presence of dark matter accounting for less than 0.1%. As these stars grow, they accumulate matter from their surroundings, transforming into supermassive dark stars, with masses of up to 1 million suns and luminosities exceeding 10 billion times that of our Sun. At the end of their life cycle, these supermassive dark stars may evolve into the supermassive black holes we observe in the universe today and in distant galaxies. By studying the fluxes and spectral properties of high redshift galaxies observed by the James Webb Space Telescope, astronomers have identified 3 potential candidates for dark stars. One key distinguishing factor between a dark star and an early galaxy lies in the presence of a specific helium isotope absorption line in the case of dark stars. If astronomers detect a spectral line in the spectrum of any of the 3 candidates, it will mark the beginning of a new era in astrophysics and offer insights into the origins of supermassive black holes. This concludes the 70th episode of the Sunday Discovery series.